Okay, so this is the second part of my intro to definite integrals. So in the last video we talked about how we were doing rectangular approximation for the area in the curve, and we got to the point where we realized that this area under the curve is also, we can use the antiderivative to find that same area, okay? And the way we do it is we use the definite integral, okay? So this is how it works. So let's look at it this way. Let's let A, okay, capital A is the area, little a is going to be a value, and x is also a value. So we're going to find the area under the curve from A to x. So the little a represents where we're starting, and x is where we're going to finish, okay? So A is a constant. So if that is the case then, okay, this is the beginning, this is my end of my area, okay? So if I divide it into another piece, so now I've got two areas. I've got the area from A to x, this area here, and then I have another area from x to x plus h. Now h, we've talked about this before. When we did limits, in the limit equation, h is basically the change in x, okay? So a is a constant, x is greater than that constant, and then x plus h is the x value here plus a change in x, okay? So when we look at these equations now, the subscript is where the area starts, okay? And of course, in the parentheses is where the area ends, okay? So if we look at it this way, this is the area here, okay? Then this area here is this area, the red area, okay? And this area here is all of it. It's all of this area, okay? Which makes sense. If I take the first area plus the second, that's going to be my total area. And that's right here. This is the first one, this is the second one, and this is my total area, okay? So that's what this equation means. So if I have then, this is my area from A to x, this is my area from x to x plus h, so the total area from A to x plus h is that equation. That also means, by doing a little algebra, here, if we say subtract this part from both sides, minus a to a of x, okay, that means that this piece right here is equal to the total minus this piece, okay? So that's what it means. This right here is, again, part 2 is equal to the total minus area 1, okay? Again, the most complicated thing about this is the notation, okay? But basically, it's a really simple idea. They're saying, okay, well, if I have this total area, it's area 1 plus area 2. Well, that means that area 2 must be equal to the total minus area 1. Duh. Makes sense, right? So, keeping that in mind, here we go. This is the same picture, okay? This is area 2 right here, okay? From x to x plus h. Okay, this is basically what we just did, okay? So the area of this rectangle drawn under the curve would be less than the actual area, okay? So this part right here, this area from here to here and from here to here, that's the minimum area that my area can have. Basically talking about if we used an inscribed rectangle. Then this height here, from here to here, with the same width, is the maximum area that it could possibly be. So my actual area has to be somewhere in between, okay? So the short rectangle, this is my minimum, is got to be smaller than the actual area, and the tall rectangle is bigger than the actual area. And remember, h is nothing more than change in x. Okay? All right. Now, plugging in what I know, that means the height, okay, or the h, the change in x, so this is area, is less than this area, but h times the max is bigger. So this is length times width. Okay, again, this is nothing more than the width times the height. This is the width times the height. And this is area. Okay? They're all areas. Right? Now, what I've done here is I've divided everything by h, all three terms. So divide this by h, divide this by h, divide this by h. H is divide out, h is divide out, leaves me with this. Okay? Here we go. So that's the same equation. Okay? Now, as h gets smaller, okay, f and the minimum f and the maximum f get closer and closer together. Okay, so think of it this way. If we go back to the last slide, okay, here, as this distance from here to here, this gets smaller. That means this point here and this point here start getting closer and closer together. Okay, so if I start bringing this in and we go here to here, or here to here, or here to here, these 2 points are going to come and meet each other. Okay, that's what we're saying. So as h, that change in x, gets smaller and smaller, the minimum and max get closer and closer together. And if we take that h, do you see it yet? If we take the limit and say, okay, we want h to approach 0, do you see it yet? Some of you guys might see it. Then that means this is the area between those divided by the height will give me the same value, f of x. Because again, this and this are going to get closer and closer together, so close that they're going to practically be the same height. Okay? Now, this is the definition of the derivative. Do you remember that equation? Remember? F of x plus h minus f of x all over h. Oh, this is the definition of the derivative. So, basically, we're talking about this. So I changed my definition of the derivative to this. Okay? Because this is my f of x. So the derivative of f of x equals f of x. Well, but I don't want the derivative of the area. So the opposite of the derivative is the antiderivative. And the antiderivative of little f is capital F. Plus there could be some constant. So now my initial value, just like when we solved for c before, my initial value is a. Okay? This is where I'm starting. My initial value is a, so I plug in a for x. Okay? Now the area from a to a, that's 0, because you can't have any area if you start at a and finish at a. So that means 0 equals f of a plus c, which means c is equal to negative f of a. We plug that in. So that means this is saying the area from a to x equals the antiderivative here at x minus the antiderivative at a. And that right there is the area under the curve from a to x. It's the antiderivative at x minus the antiderivative at a. And when we put all of this together with our definite integral, this is how you evaluate it. So the area, and this is again the integral. This is start. This is finish. Height, width is equal to the antiderivative of f. So whatever f is, if you take the antiderivative and you plug in b and subtract the antiderivative when you plug in a, that will give you your area from beginning to end. Okay, and this is something we're going to be using a lot. It's actually part of the fundamental theorem of calculus. Okay, so example, going way back. Okay, so if I wanted to find the area under the curve from 1 to 2, okay, basically I want to find this area right here. Okay, to set up my integral, my definite integral, I'm starting at 1, I'm ending at 2. Okay, so that's the way it is. So my function f of x is x squared dx, beginning at 1, going to 2. Okay, based on what we just learned, we are going to first find the antiderivative. So the antiderivative of x squared is 1/3 x cubed. This is the integral evaluation line. Okay, so it keeps my limits, my upper and lower limits. So this goes there and that goes there. And then we plug in the 2 first. So it's going to be 2, plug in 2 minus the antiderivative when you plug in 1. And you're going to get 8/3 minus 1/3, which means the area from 0 to, the area from 0 to 2. Okay, and this is the whole reason. This represents the area from 0 to 2. So all of this area here, all of it is 8/3. Okay, this area right here, that is 1/3. So we have to take the integral gives you everything from 0 to wherever you end if you don't tell it to back out the other part. And that's what we were just talking about that. Okay, so we have to subtract out the area that we don't want. And that will give us our actual area. So the area under the curve from 1 to 2 is 7/3. This, like I said, this is the area from 0 to 2. But we don't want the area from 0 to 2, so we have to subtract the area from 0 to 1. So that we only get the area from 1 to 2. Okay? That's how it works. That is the definite integral. Another way of looking at it, using some trig, same thing. Find the area between the x-axis and the curve of y equals cosine. And I know you guys love trig. So I've got to break it up into 2 pieces. Okay? Because it's asking me to find the area between the x-axis and the curve. Well, if we do this area here and this area here, okay? If I had done it just from 0 to 3 pi over 2, it would have given me displacement, not distance, and it would have turned that area negative. So I had to split it up so that it would become positive. But it works just the same. So you take the antiderivative cosine is sine, and the antiderivative of this cosine is sine, and we're subtracting them. Then we evaluate this one from sine of pi over 2 minus sine of 0. So it's the top one minus the bottom one, minus this one, the top one, minus the bottom one again. So this one and this one. And then you got to know your unit circle. And you get 1 minus 0 minus negative 1 minus 1, which means your area is 3. But that also means that it's telling me this right here is the area from 0 to pi over 2. That's this piece right here. Okay? This part right here represents this area here. Okay? So this area right here is 1, and technically this area right here is -2. That's why here, if you had done this, it would have been 1 minus -2. If I had done it all the way, if I had done 0 to 3 pi over 2 of cosine x dx, that would have given me -1. Okay, so you got to be careful. Depending on how they ask the question, I want to find all the area between the x-axis and the curve. It's telling me I want to know all of the area, the total area. Okay, so you got to be careful. When you think about it in velocity versus position, the area under velocity is displacement. So when you have negative or below the x-axis, it's going to subtract it. Okay, so you got to be careful. But that's definite integrals.